Hi folks, Mr. Long here. We're going to talk in this screencast about derivatives of ln x. So we know that ln x is just like any other logarithmic graph, and it has an x-intercept of 1, and it has a vertical asymptote at x equals 0, and it has a positive slope. So there is an algebraic proof for the derivative of ln x, but I'm not going to go over that. That's in the notes that I've posted, but I'm not going to go over that proof right now. Let's rough sketch some tangents though. So we got a tangent there and a tangent there. So if I go to this one here, what is the slope of that tangent? Well, oh, by the way, slope of the tangent is the derivative, right? The tangent slope function. So the slope right here is positive and very, very big. So it's, let's see, it's up here, right? And then if I did this tangent here, that tangent has a positive slope and it's kind of a medium slope. And then out here, the tangent's getting really, really, I should be using a different color than that, shouldn't I? The tangent slope is getting much, much flatter. So it's sort of down here. So if we were to draw the graph of the derivative of ln x, that does look like a reciprocal function. We know that much. But in fact, what it is, if y equals ln of x, y prime is actually 1 over x. But notice x has to be greater than 0. And that's because normally if you were doing the graph of 1 over x, it would have a branch over here as well, right? But this one doesn't because you can't take a derivative where there is no function. And the graph of ln x only exists to the right of x equals 0. Okay, so if y equals ln x, the derivative is 1 over x. And then we have chain rule applications, of course, too. All right, so that's the development of the rule graphically. As I said, the algebraic development is in the notes. So let's do some examples. Okay, so the derivative of ln x, number 1 here. The derivative of ln x is 1 over x, x greater than 0. Okay, now what we're going to do here is, and g is the inside derivative, so we're doing number 2, and that's inside prime, f is the outside function, and then the outside prime. So the inside function is very clearly 2x to the 4th plus 3. How do I know it's a chain rule, by the way? What I notice is that's not an x. As soon as the argument, which is the part that's inside the brackets, is not x, I've got a composite function, a function inside a function, and I need the chain rule. So the inside prime would be 4 times 2 is 8, 8x cubed. And then the outside function is ln of, I'll just put an open bracket, so ln of open bracket, and the derivative of that is 1 over the bracket, okay? So I'm just reducing my amount of writing. I could put ln of like g or ln of u if I call the inside function u. All right, and then to get my derivative, I multiply those together. Okay, I multiply those together. So what I need to multiply together is 8x cubed and 1 over brackets, and brackets is the inside function. So on the numerator, I'm going to have 8x cubed multiplied by 1. So that's going to be 8x cubed over 2x to the 4th plus 3. Okay, and that is our derivative. So that's the chain rule. Well, now let's do the quotient rule for ln x over x. So this is where we have top, bottom, top prime. You know what? I'm going to do something that one of the students suggested was he didn't suggest to me, he was very humble, I just noticed that he did it. He did top prime, bottom, so sorry, did top prime here, bottom here, and then top, bottom prime here, because we know the derivative is top prime bottom minus top bottom prime all over the bottom squared. So it made life a lot easier in terms of writing out your derivative. So we know the top is ln x. We know the bottom is x. Okay, so you start that way. So the top prime is then 1 over x, and the bottom prime is 1. Okay, so I'm looking at x, I'm differentiating that. The derivative of ln x is 1 over x. And now instead of doing a crisscross like I was showing you, you just multiply those and separate them by a minus sign. Okay, so that's going to equal, I'm going to go to a color that's a little easier to read than that green. So it's going to be 1 over x multiplied by x, which is just 1. So 1 minus, and then top ln x times 1 minus ln x, okay? And that's all over the bottom squared, which is x squared. Okay, so I can write that as y prime if I want. Okay, so that's the quotient rule. Now what we're going to do is graph sketch that particular function. Okay, graph sketch that particular function. So when we go to graph sketch that function, first thing we need to think about for this one is the domain. So anytime you have square roots, anytime you have ln, you need to think about your domain, because not all x values will be allowed. So when are you allowed to have x values for ln x? Well, you can't take the ln of a negative number. Why is that? Because remember that another way of writing ln x is e to the y equals x, right? That's equivalent. That's the same function. It's just this one is written in a way that you can't write it as a function, because you can't write it as y equals. So, but those are the same relationships, okay? So if I think about that, can I ever get a 0 value for x? So y represents the number of times I repeatedly multiply or divide by e, 2.718. Okay, so if I multiply by e over and over again, that's positive exponents, can I ever get to 0? 2.718, or think of 2.7 times 2.7 times 2.7 repeatedly. Will that ever be 0? No. What about if I divide by 2.7? If those are negative values, will I ever get 0? No. Okay, I can have a 0 there. If I get e to the 0, that's 1, right? So that's 1. So there is no way that that's a negative or 0. Well, that's your domain, right? That is your domain. So we know that x has to be greater than 0. Okay, so what about intercepts then? So for an x-intercept, we know that x is greater than 0. So since x is greater than 0, that clearly indicates there's no y-intercept. Right? Not possible. Not possible. So what about an x-intercept? So if I said ln x over x equals 0, that would give me an x-intercept. Right? So ln x over x equals 0. I would multiply both sides by x, and I'd get ln x equals 0. So I can rewrite that as an exponent. And that means the base is e, the exponent is 0, and that equals x. X equals 1 is an x-intercept. Okay, x equals 1 is an x-intercept, which makes perfect sense, because ln x has an x-intercept at x equals 1. Okay, so we have our intercepts and our domain. So again, we need to check domain when anytime there's a restriction on x values. Okay, that's when you check your domain. All right, let's look at our end behavior. So the furthest we can go to the left is 0, but we can't actually go to 0 because you can't take the ln of 0. So I'm just going to do this by writing like 0.01, like that, just as an approximate value. Okay, so then that's going to be ln of 0.01 divided by 0.01. Okay, what does that equal? Well, let's go to our calculator and see. Okay, so that is negative 460 or so. So that means there's a VA at x equals 0. Now what about far to the right? Well, I could put something like 1,000 in, right, for x. So if I put 1,000 in, I'd have the ln of 1,000 over 1,000. Well, if I think about this, okay, let's think about this for a second. So what does ln of 1,000 mean? What exponent do I put on e to get 1,000? So how many times do I have to multiply e 2.7 something repeatedly to get 1,000? Well, that's going to equal, if you think about this, you're going to need, and the exponent on 2.7 is clearly going to be a lot less than 1,000. So that's much smaller over something that's much bigger. And as we move out to infinity, we're going to get closer and closer and closer to 0. Okay, so really this is a limit, right? These are when we're doing end behavior, we're always doing limits. So now if you want to put that in a calculator, you can. It's going to be very close to 0. Because I want you to think about this. 2.7 for e is very close to 3. So it means approximately 3 to what exponent equals 1,000? Well, 3 to the 1 we know is 3. 3 to the 4, for example, or 3 to the 3 is 81. 3 to the 4 is 243. 3 to the 5 is greater than, no, it's 3 to the 6 is greater than 1,000. Okay, so really what we're going to do is we're going to have a number here that's, say, maybe 7 over 1,000, right? So that's going to be much. That's going to be like the top is much smaller than the bottom. So really, this is going to approach 0. So that's going to mean we have a horizontal asymptote at y equals 0. Okay? And again, you can use your calculator for that as well. We're going to talk about how to do limits like that later when we learn something called L'Hopital's rule, which I will teach you, even though it's not in the Ontario curriculum. For the AP folks, you have to know it, and if you're not an AP, it's just something that's worth knowing. But you have to understand why it works. Okay, finally, so we know our end behavior, we know our vertical asymptote, we know our horizontal asymptote, we know our x-intercept. Now we need to know our stationary points. And we already got the derivative. So we know we want to set the derivative equal to 0. The derivative from the previous question was 1 minus ln x all over x squared, and that has to equal 0. So when is fraction 0? When the top is 0. So 1 minus ln x is 0, or ln x will equal 1. Again, rewrite it as an exponent. E to the 1 equals x. So the stationary point is at x equals e. So is that stationary point a minimum or a maximum, right? That's what we have to figure out. And that's, again, that's tough because it's 1 minus ln x. So let's think about what that looks like. In terms of our, so what we want to do, again, if possible, is we do our related polynomial, p prime, which in this case it's not a polynomial because it's ln, but think about your sign change. So here's your derivative right here. Can x squared ever change signs? No, it's now it'll be a double x-intercept at 0, so we should include that. So what is our related polynomial? Our related polynomial, well, that's at 0, and we know 0 is not even in the domain, right? So really, we don't have to use that because 0 squared is not in the domain. So what we have to do is we have to look at 1 minus ln x and see, we know the solution to that is e. So the x-intercept is e. So we've only got one x-intercept, it's at e. So I have to know whether what that graph looks like. So let's think about that for a second. So what does the graph of 1 minus ln x look like? Well, I would rewrite it as y prime, or p prime rather, because we're forgetting the x squared in the bottom, would equal negative ln x plus 1. So it's ln x that's reflected right? It's reflected because of that negative, and it's shifted up 1. So really what it looks like is, a regular ln x graph looks like that. So a reflected ln x graph looks like that, except it's lifted up 1. Okay, so your ln x graph is going to look like, or rather your 1 minus ln x looks like that. Okay, so that's 1 minus ln x. Now, the other option, of course, is just go to the left and to the right of e. Okay, to the left and to the right of e. So, like so. X and y prime. So we have e that's 0, right? So, and we know e is approximately, say, 2.7. So here I might do 2.6, and here I might do 2.8. So I have to do 1 minus ln of 2.6. And we know the ln graph, right? We know the ln graph. So, well, let's actually just put this in our calculator. So 1 minus ln x. Here. So 2.6 we found was negative. This was positive. So that means that our function was, oh, whoops, did I do that backwards? Let's see. To here, 2.8, sorry. That's negative, and that's positive. Okay, so what did I do in this table? In this table, I know that the E was a stationary point. E is very close to 2.7. So that means the slope when x equals about 2.7 is 0. So I want to check just to the left and just to the right to see what the derivative does. I don't have to worry about the bottom. The bottom is x squared. That's always positive. So I just did 1 minus ln x. So from the graph, I could have gotten that that's positive and that's negative. Okay, so again, the curve goes up, over, and down, so that's a maximum. All right, finally, let's make our sketch. I'll put it down here. So what information did we have for this one? We knew that there was a vertical asymptote at 0, and we knew it went down the asymptote. We know there was an x-intercept at 1, and we know E is about 2.7. There was a maximum. So, and I also knew there was a horizontal asymptote at 1. That's x equals 0. Whoa, y equals 0, and that's x equals 0. Okay, so it goes up, like so, to there, comes down, like so. Okay, so that's what that graph looks like. And there you have derivatives of ln and also graph sketching with ln. Again, go over this video, make notes, etc. Okay, have a great day. Oh, there, sorry. So I was thinking it wasn't going to that page. Okay, so function, whoops, I want to get to there. So the function, and we're going to do ln of 0.01 and bracket, divide that by 0.01. Okay, ln of 0.01 divided by 0.01, and that's negative 460, as you can see. So that's pretty clear that we have a vertical asymptote, right? So if you're at x equals 0.01, then you're way, way, way down at negative 460. So I would just go one minus ln 2.6 is negative, oh no, that's 26. Negative 2.6. That's 0.044. That's positive. Okay, so 2.6 is positive. 2.8 is negative. Okay, so let's go back. 1 minus ln 2.8 is negative. Yeah, sorry. So I'll go